great. If you don't have them and want to print them out, you only need to print out for probably 13.1 for the time being. Let's brighten up a little bit. Okay, what we're going to talk about in chapter 13 is graphs and the derivative. The one thing I want you to understand about chapter 12, and I think some of you are still struggling with this, a derivative is a formula for slope, okay? That is actually what a derivative is. It isn't that big long process that you go through. It isn't a end to itself. It's a means to solving a problem. But it gives you the slope of a function that isn't linear at any point on that function. You don't need a formula for slope with linear functions because linear functions have the same slope everywhere on that function because it's linear. That's what makes it linear, is the fact that it keeps the same slope all the time, the same rate of change. But if you've got a quadratic function, it's changing faster at some times than it is at others, and it actually changes direction, which a linear function doesn't. So other functions that are curved, they have slope, but it isn't the same slope all the time. Okay? So what the derivative is a means to finding the slope of a function, meaning its rate of change. And you've got to get straight in your head that what a rate of change is either an average rate of change from point A to point B on that slope, and that anytime you say rate of change, it's always something per something in an application problem. Dollars per pound, cents per ounce, dollars profit for selling X computers. But it has to be dollars per computer, dollars per pound. It has that word per has to be in there. That is part of a rate of change. That's the definition of what's. You've always thought a slope is rise over run because that's what they told you it was in algebra. But slope is really the change in y with respect to x. And that's what slope is, and that's what a derivative is. Slope and the derivative are the same thing. So in an applications problem where you're told to take a derivative, your derivative is giving you the change in the function at any given point in time. So when you're turning in your applications for chapter 11, I hope you realize that when you were writing those interpretations, you had to explain to me what that number meant. I mean, the arithmetic, that's great. You can get the calculator to do arithmetic all day long. Y'all are going to be in business. Otherwise, I don't know why you're here, because nobody would take this class just, for fun. They're taking this class because they want to be a business major. And there's a couple of things you need to realize here. Number one is, yes, math does figure, as you've gotten now, a big face full of it, that math does figure heavily in business. You can't ignore it. You can't get away from it. You've got math to do in business. It is not a business is not a math light major. The only major at this school that has more math in it than yours is engineering. The second thing you've got to get, and this is even more important to you because you're business majors, you have to learn to communicate in reading and writing. If you walk up to your boss when they've asked you for a report on the profits over the last quarter for your division, you can't walk up and say, well, here's the rate of changes for all these different lines, because your boss is going to look at you and say, the what? What are you talking about? Well, this is the slope of all these functions. Can you put that in English? Okay? He's going to want you to say, the rate at which my profit was increasing when we were selling 600 pounds of potatoes was the profit was increasing by X number of dollars per pound of potatoes that we grew and sold. Okay? And I hope nobody in here did this, and I may be letting the cat out of the bag for those that are going to turn this in later, but when you do that last problem, folks, and I hope my guys in the other class kind of hear this. Hundreds of dollars in profit per pound of potatoes doesn't make sense, because you can't have hundreds of dollars per pound of potatoes in profit when the potatoes don't sell for even more than dollars per pound. They might sell for a couple bucks a pound, but that's it. So always, the last thing I want you to be very, very careful to do is to always look at the answer that you've got numerically and look at the problem that you got it in and say, does this make sense? Is it logical that this answer would be right? So remember, this is applied math. Arithmetic, calculator does that. You've got to tell me what the meaning of the numbers are the calculator gives you. Okay? So with that said, we're going to talk a little bit about some more derivatives, but more about how they're used. The graph on the next slide I'm going to show you shows the relationship between the number of sleep-related accidents and the traffic density during a 24-hour period. The blue line is going to show the hourly distribution of sleep-related accidents. The green line is going to show the hourly distribution of traffic density. In other words, how bad is traffic? Is it rush hour, or is it kind of, you know, like slacked off because it's mid-morning? And then the red line is going to indicate the relative risk of sleep-related accidents. And for example, the relative risk graph shows us that a person is nearly 7 times as likely to have an accident at 4 a.m. than at 10 p.m. So the time of day, this would be at midnight. At midnight, there were quite a few accidents. The relative risk was lower than the number of accidents, though, and traffic is obviously light. So there were quite a few accidents, but that wasn't where most of the accidents occurred. Accidents actually peaked out at around 5 or 5:30 in the morning. More accidents early in the morning. Now think about why that would be. 5:30 in the morning, and people are sleepy, and traffic is what? It's starting to pick up, right? Would you be more likely to have an accident? You're on your way to work, traffic's heavy, you got some sleep, but you're still tired a little bit maybe. Yeah, especially if you're one of these people that has to work long hours and doesn't get enough sleep at night. So if you look back at what this is talking about, you can see that the relative risk of having an accident at, let's say, 9 or 10 a.m., that's pretty low. But the reason for that is because even though the traffic is at a higher number, higher relative density, you have fewer accidents because there's less people on the road. You have fewer accidents that are sleep-related because even though there's more people on the road, you have fewer sleep-related accidents because by mid-morning you're awake. The sleepy people aren't on the road. The people that have got their caffeine, they're on the road by then. And notice that the place where your risk is highest is, as it says, in the small hours of the morning when people are sleep deprived, and even though traffic density is low, there's a lot of sleepy people on the road. Okay? Now that's a realistic example of what someone in risk analysis for an insurance company would look at. They would look at those things. Now the idea here is when you want to look at when there is a maximum or a minimum. Like we looked at on here, the maximum risk was in the early hours of the morning. The traffic is highest, looks like at around, let's see, 18 hours into the day, that'd be about 6 p.m. That makes sense. And then the next highest is around 8 and 9 in the morning. That makes sense. But the sleep-deprived people, the sleep-related accidents happen more often in the not early morning accident time, but kind of like daybreak. And then it drops off real sharply, probably because the people that were working till midnight, they've gotten home and gone to bed by now. So by 9 or 10 or 11, there's not that many. But then again, why would your sleep-related accidents go up at around 2 o'clock? Who's going to work at 2 o'clock in the afternoon? Second shift. And second shift, people that work second shift a lot of times have sleep disorders because it is not a normal human body rhythm to go to work and to start your day at 2 o'clock in the morning. It's more normal for human beings to rise in the morning and go to bed when it gets darker because that's what your natural body rhythm is supposed to be. But we've learned to deal with body rhythms that don't work that way, but not as well as we probably need to. And notice that at the time that the sleep-related accidents is the lowest is down here, let's see, 20, so that's 8 o'clock. Everybody's at home or at work, one or the other, and they're not on the road. They're not on the road sleep deprived, although there is a lot of traffic around that because people are going out to dinner and whatever and heading home after that. So the goal of this chapter is to talk about when are functions increasing, which means when are they approaching a maximum, when are they decreasing, or when are they approaching a minimum, and do they ever stand still? Do they ever flatten out? And a lot of times they do. These three graphs, even though they're very, very different functions, all share one thing. And that is that they are all increasing. Meaning as you read from left to right, the graph is traveling uphill. So those are all increasing graphs. This is math language for what I just told you. As x approaches infinity, which means they're increasing, then f of x values also approach infinity, which means they're increasing. Both things go up. These three functions, and again, they're very different functions. These three functions all share one characteristic, and that is that they're all decreasing. As x gets larger, the value of the function becomes smaller. So there's the math way of saying in common sense, if you're at point A on the line and you go to point B on the line, which is further down the line than point A, and you're higher when you get to point B than you were when you're at point A, well, then the function's increasing. To which, you know, most English-speaking people would look at that and say, I don't know what that says, but I know what it means to go uphill. Okay? So don't worry about memorizing this. Worry about knowing when things are increasing or decreasing. So let's practice a little bit. This is a function. I don't know what it's modeling, but this is a function. It's a function because it passes the vertical line test. It only has one y value for every x value. Where is this function increasing? What parts of the function are increasing? Okay, exactly. Negative infinity to negative 4, because as you come from negative infinity on the x and you keep climbing, when you get to negative 4, you've kind of hit a peak. Where else is it increasing? From 4 to 6. okay? So those are the intervals on which it is increasing and decreasing. Now, I am not going to be real picky and real persnickety about if you write it in interval notation that you use parentheses or if you use square brackets or anything like that. If you want to tell me in English, it's increasing when x goes from 4 to 6. Okay, that's fine. Tell me in words. I want to know if you know what it is, not fancy notation. Where is that function decreasing then? Okay, from -4 to 0, and from 6 to infinity. Okay? Like I said, I'm not real picky about whether, you know, the brackets or the parentheses. This is parentheses because the reason I put the parentheses is because you're actually leaving out the -4 and the 6, because what is happening at -4 and at 6? Is it increasing or decreasing? Neither one. It's stopped. Okay? It's about to change directions. It's sitting at the corner and about to head the other way.
Will the correct notation be the square bracket? Is that the infinity?
No. No, and the reason it's not is because infinity is not really a number. I mean, I'm not going to beat you up if you put a square bracket on it because that's not a critical thing for you to know. Oh yes, my math lab will.
That's what I need to know.
But if you did it and you don't want to bother with having to go back and work a whole nother problem, just hit ask my instructor, or you know, send me a message and say, well, you please give me credit in problem number so and so because my math lab is being stupid again. Now that'll be fine. Now, we didn't talk about the interval from 0 to 4. What is the function doing from 0 to 4? It's remaining constant. It's not increasing, it's not going uphill. It's not decreasing, not going downhill. It's flat, if you want to look at it that way. What I want you to do is think of functions as being kind of like a roller coaster. When the little roller coaster car is going up to the top of the hill, when you're starting to hold your breath because you know it's fixing to get to the peak, okay, that's when the slope is positive because you're going uphill. When you get to the peak, what happens? No, you suck in lots of air so you can scream because you're fixing to go, phew. But yeah, it's 0, okay? And when it hits those flat places, whether it's at the top of the hill or the bottom of the valley, it's 0. So what happens here is this function's slope is positive, 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 0. Slightly negative, but negative, 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 0. Then it starts to be positive again. And then there it goes to 0 again. And then it becomes sharply negative. It's very steeply negative on the other side. Okay? Anytime your slope goes from positive to negative, what has to happen in between? At some point between the positive slope and the negative slope, it has to have a slope of 0. And somewhere between a negative slope and a positive slope, it has to have a slope of 0. Because you can't go from negative numbers to positive numbers without passing through 0. And you can't go from positive back into the negative numbers without passing through 0. So there's the math language for what we said in common sense, which is why you're taking this class and not the engineering calculus class. Now, I am going to talk to you about what a critical number is. Critical number are the numbers in the domain of a function where the function's value, the function's derivative's value, more importantly, the function's derivative's value are either 0 or it doesn't exist. Either the derivative has a value of 0 at some point, or it doesn't exist, and that makes it a critical number. A critical point is the point where the x-coordinate is the critical number for that function, and the y-coordinate is whatever the value is of that number. In other words, it's going to be whatever you plug C in to the function, and you come out with a number for it at the end. So I'm going to back up for a second. This function appears to have a critical number at about 1, let's say 37. Okay? It has a critical point at about 137. That's that first peak. That's where its derivative is going to be equal to 0, because its rate of change went from positive to negative, so for just an instant it was 0. So that's a critical point on that function. It has another critical point right there in the neighborhood of 2, because it goes from being negative just for an instant at 0 before it starts climbing again. So what that critical number is would be probably about 2, maybe 33, 34. And again, all we're doing here is guessing at the y-coordinate, because we don't have anything better than that to do. We don't have a better way of telling. This function has another critical number at about positive 4, because that's where it's hit another peak. And that critical number is 4, I'd say about 65. Its critical point has both coordinates, but its critical number is the x number. Okay? We're going to use a derivative test to figure out when the function is increasing and decreasing. And the reason we're able to do that is because, remember, the derivative represents the slope of the function. So when the derivative is positive, the function is going uphill. When the derivative is negative, the function is going downhill. When the derivative is 0, it's either changing from going positive to negative, or it's changing from going to negative to positive. So what we're going to do is we're going to look at this function, and we're going to look at where it's increasing or decreasing, which means we're going to locate all the places on this graph where the tangent line would be horizontal, meaning it has a slope of 0, meaning that that's where the derivative is 0. Okay? And then we're going to graph the function. Now we could just plug the function into our calculator and graph it, and we're going to do that after we check that we're right. So here's how we start out to do this. And the reason that I left the 5 problems that I did in the assignment was because the 5 I left in there, all but one of them are factoring problems. Sometimes it's easier, easier to factor and figure out where something is equal to 0 than it is to use quadratic formula. Now, if you don't instantly see how to factor a problem and it's quadratic formula is fine. It'll find the same thing for you. This happens to be a cubic, though, and so factoring is a little tricky until you realize that you've got to take the derivative. You're not really interested in where the function is equal to 0. You're interested in where the derivative is equal to 0. And the derivative of x to the third plus 3x squared minus 9x plus 4 is, drop the 3 down in front, reduce the 3 by 1, so that's 3x squared. Drop the 2 down in front of the 3, 2 times 3 is 6, to the times x to the first power. And then the 1 that's on the negative 9x for an exponent. 1 times negative 9 stays negative 9, but when you say 1 minus 1, that's x to the 0, so the x drops out, and the derivative of the 4 is 0. So that's why I said there's nothing really terribly new about this. You could take the derivative of this. In fact, you're going to on your next test. Maybe not that exact function, but one just like it. So you take the derivative, and we want to find the critical numbers, which is where the derivative is equal to 0. So you take the derivative and you set it equal to 0. Now, the way they did it was they factored out the constant 3, because 3 goes into 3, 6, and 9. And that left us with x squared plus 2x minus 3. And x squared plus 2x minus 3 does factor into x plus 3 and x minus 1. But just as a reminder, because not everything factors, is that better or worse? I think that's better. A is 3, B is negative 6, C is negative 9, x equals minus b plus or minus the square root of b squared minus 4ac over 2a. The opposite of negative 6 is 6. Negative 6 squared is 36. 4 times negative 9 is positive 36. Oh, so what?
4 times negative 9 is negative 36.
Right, okay, yes, sorry. Let me leave it at that. 4 times negative 9 is negative 36 times 3 is how much? $108, right? And it's negative 108 over 2 times 3. Or, since we paid a lot of money for this thing, this actually turns into 36 plus 108, which turns out to be 144. And 2 times 3 is 6. And the square root of 144 is 12. So we have 6 plus 12 and 6 minus 12, both over 6. Since 6 plus 12 is 18, and 18 over 6 is 3, 6 minus 12 is negative 6, and negative 6 over 6 is negative 1. X is equal to 3 and negative 1, which is exactly what they got by factoring. So if you don't want to bother with trying to factor, you don't have to. You can always use the quadratic formula. I'm looking for this. I don't know if this one has a solver or not. No, it doesn't seem to, so we'll let it go with that. Okay? So just remember, and I will remind you of this several times as we go through this when they factor. If you're not really good at factoring, that's okay. You have quadratic formula, and that's the only thing they ever really make you factor, unless it's something that is like factoring out a greatest common factor. So x equals -3 or x equals 1. That means f of x has a critical value at x equals -3 and x equals 1. It means that the slope of f of x at x equals -3 and at x equals 1 is 0. And if you have a slope of 0, that means that it either bottomed out and reached a minimum, or it topped out and reached a maximum. And in between, it was either increasing and then decreasing, or decreasing and then increasing. So the way we figure out is we find the critical numbers. And as I said, we know that it has a horizontal, as in slope of 0, tangent at those two numbers. And there are no places that f of x doesn't exist, because there's nothing there where it would ever cause it to divide by 0. We're not ever going to take the square root of a negative number because it doesn't take square roots. So it's always defined, then those are the only two critical numbers there are, is -3 and 1. So what we're going to do to determine when it's increasing and decreasing is we're going to draw a number line, and we're going to put those values on a number line, and then we're going to see is the function positive or negative in between. So here's what we do. And rather than just show you the picture, I'm going to come over here and actually show you the function. So my original function, go back and make sure I copied it right, is f of x is x cubed plus 3x squared minus 9x plus 4. And from that original function, I'm going step by step. I'm going to find f prime of x, which was 3x squared plus 6x minus 9. And when I set it equal to 0, I found out that x was equal to -3 and x was equal to 1 when the derivative was equal to 0. So that made these the critical numbers. And I want to know what is happening to the slope before and after -3. So in order to find out what it is before -3, I'm going to take f prime of -4. So f prime of -4 is -4 squared is 16, and 3 times 16 is 48. 6 times 4 is 24, and it's going to be negative because the 4 is negative. And then minus 9. And if I combine -24 and 9, I get -33, and since 48 is bigger than 33, I don't really care what it is. I only care that it's positive. Okay? It's a positive number. That means on this side the slope was positive. And since this is bigger than -1, I can look and see what it's doing at 2. Two squared is 4, 3 times 4 is 12, 6 times 2 is 12, 12 plus 12 is 24, and I know 24 is bigger than 9, so I know that's positive. Slope's positive here. So in between, I'm kind of expecting this to be negative, so that it goes positive to negative and then negative back to positive. But I'll check. F prime of 0 would be 3 times 0 squared plus 6 times 0 minus 9. And that's 0 and that's 0. So it is indeed negative. Okay? So here's what I know is happening on that graph. I know that on the interval from negative infinity to -3, that graph is going up. I know that on the interval from 1 to positive infinity, it's going up. And I know that in between, it's coming down. Now, you've graphed cubic functions before. Tell me what a cubic function looks like. Quadratic functions are either a U shape or an upside down U. Cubic functions either have a hump and then a valley, or a valley and then a hump, right? This one's going to have a hump and then a valley. Okay? And we can verify that by graphing the original function. And we will need to see at least from, let's say, about -5, since it's less than -3, to about +5, since that's bigger than 1. And I'm not going to change anything else. After I figure out that I need to go from less than -4 to more than +2, all I have to do is hit zoom. Fit. And I might not get a perfect picture immediately, but I got one at least I can see that whole graph in. So what does it do? Did it come to a peak over -3? And looks like it came to a valley at +1, which is what we thought it would do. Okay? So that's why you draw that number line. You use the numbers in between those dashed lines, which are the critical numbers, and then plug them into the derivative to see if the derivative is either positive or negative, so that you know if the function is going up or going down, knowing that it hits a peak or a valley at those critical numbers. And our function looked like that. So what that means is that our slope was positive from -infinity until it got to -3. And at x equals -3, the tangent line had a slope of 0. The slope of the function at that peak is 0. And then from -3 until we get to +1, the function is decreasing because its slope is negative. And then at -1 it turns and it becomes positive again on its slope, so it's increasing. And it'll continue to increase after that because it only has 2 critical numbers. It doesn't have any more critical numbers. So right there, you're seeing everything that function is going to show you. You don't need to see any numbers outside of the domain we're looking at, from -4 to +4 even. We know what that function's doing. It's not going to change anymore after that. The rest of the time, it's going to go down forever and up forever. Okay? So let's look at another one. You're going to find the critical numbers, decide where the function's increasing and decreasing. If f of x is equal to x minus 1 to the 2/3. Now, I don't see any factoring that I know how to do here. Okay? So here's your first step. You got to take the derivative. And when I take the derivative, I bring the power down in front, that's the 2/3. And then I reduce the power by 1, and 2/3 minus 1 is -1/3. And then I take the derivative of x minus 1, because remember this is chain rule problem. But the derivative fortunately is 1, so it doesn't really matter much. And I wind up with either 2/3 x to the -1/3, or in order to help me remember some things, I'm actually going to make that exponent positive and put it in the denominator where it goes. So I'm going to make a note of what the derivative is here on the paper. Now, what's the only thing I'm worried about in that fraction? As soon as I see a rational function, what's the forbidden sin that I have to worry about? Can't divide by 0. Is there anything that would make that denominator equal to 0? What? No, not 0. 1. Because what you want to do is you want to turn that into 0, okay? If you divide both, you set it equal to 0 to start with. I mean, that's always what you do. You set the derivative equal to 0. Then you divide both sides by 3, just to get rid of the 3. And then you have 0 divided by 3 is just 0. Now, technically, the way you get rid of a fractional power is you multiply or you raise it to the exponent that it's reciprocal. But common sense tells me I really don't care. I know that I can look at the problem without ever having to go through all this. If you think about it and realize that the only thing that you had to worry about was what would make this equal to 0. That really doesn't make any difference. If that's 0, it doesn't matter what those two are. If that's 0, you're up creek. Okay? So that's really what I needed to set equal to 0. So x can't be 1. The derivative is not defined at x equals 1. So that tells me the slope of that function is undefined. At x equals 1. That makes x equals 1 a critical number. okay? Because remember, your critical numbers are either whether the derivative is equal to 0 or where it's not defined. So that critical number is 1. The truth of the matter is this thing can never actually be equal to 0. You can try to set f prime of x equal to 0. But it never happens because you cannot take the number 2, and I don't care how big you make x, you can make x get as big as you want it to, or as negative as you want it to. This is never going to be big enough or small enough to turn that into 0. Doesn't matter how you cut 2 up, there's always going to be little pieces of it. It's never going to turn into 0. So that derivative is never going to be able to be 0. Okay? That means that x equals 1 is the only critical number we have for that function. And that makes the rest of the problem easy to do. Because if x equals 1 is our only critical number, we just need to see what the function's derivative is on either side of that. And on the left-hand side, we have x equal to 0 because 0 is to the left of 1. On the right-hand side, because we don't want to pick big numbers, we like small numbers, we'll test in 2. So f prime of 0 is 2 over 3 times 0 minus 1 to the 1/3 power. 0 minus 1 is negative 1 to the 1/3 power. And 3 times negative 1 to the 1/3 power is the same as saying 3 on the cube root of negative 1. And because negative 1 can be tripled, then basically the cube root of negative 1 is negative 1. And 3 times negative 1 is negative 3. So f prime of 0 is 2 over negative 3. And it's definitely negative. So the function's going to go downhill. Okay? Until it reaches 0. Or excuse me, until it reaches 1. Then it's going to be flat. So then the next thing we say is, okay, well then it must be going to go uphill after that. But we have to verify it anyway. So we're going to plug in 2. I'm going to scoot over a little bit so I can work over here. F prime of 2 is 2 over 3 times 2 minus 1 to the 1/3. And that's 2 over 3 times the cube root of 1, which is 2 over 3 because the cube root of 1 is just 1. And that's positive. So yes, it goes back up. So here's what we know happens. The function is decreasing until it comes to x equals 1. And then just for an instant, it has a slope of 0. And then its slope becomes positive again. Okay? So let's graph the function and see if we're right. Remember, our original function was x minus 1 to the 2/3 power. Always put your fraction, exponents or anything else they're in, always put your fractions in parentheses. And that window will do just fine. But I'm still going to do a zoom 0. There it is, it's coming down. What do you notice happened to the function when x was equal to 1? Change the window a little bit. Ah, that was what I was waiting for. So this is a chapter 11 concept. Can I take the derivative at x equals 1? No, because it was undefined. Does the graph show me that it had no derivative at x equals 1? It's undefined. Okay? That's why I said this chapter actually will help you kind of tie up chapter 11 and chapter 12 a little bit. So this just does what we just did, and there's the function. So the important thing to remember is that the conditions under which a function is undefined, division by 0, the denominator cannot be 0, or even roots of negative numbers. You can't take the square root or the fourth root of a negative number. And also, even though I did put this up here on the slide, you need to remember the rules for differentiability. If the derivative exists, it's going to give you the slope of the line, but it doesn't always exist. It will not exist at a place where the function doesn't exist. That should make sense, because any place where the function doesn't exist, it doesn't have a slope because it doesn't live there. Okay? The function has to have a limit at that point to be differentiable. In other words, your right hand and your left hand have to come together, and when they come together, it needs to be at the value of the function at that point, not where the function's undefined. And that you can't take a derivative at a sharp point. And there's one other place that's going to come up, and it was on the exam. You cannot take the derivative at what we call vertical tangents, because the slope of a vertical tangent is undefined. Okay? So this all ties together with what you've already learned. So let's try one more. Find the intervals for which this function increases and decreases, and then graph it. That's the same thing you're doing with all of them. So the first thing we need to do is take a derivative, right? Because we have to have the derivative and set it equal to 0 to see where the function is going to be increasing and decreasing, when its slope is positive and negative. So I'm just going to copy down the function, and y'all are going to help me take its derivative. So here's the function. What derivative rule do I need? I need quotient rule. okay? N stands for numerator. D stands for denominator. So I need to take the denominator, multiply it by the derivative of the numerator, which happens to be 1. Subtract the numerator times the derivative of the denominator, which also happens to be 1. And put it over the denominator squared. And it might be a good idea to try to simplify this a little bit. The ones don't really make any difference. But I've got x plus 1 minus x, and minus times minus is plus 1. So this tells me that f prime of x, x minus x disappears, 1 plus 1 is 2. Over 1 plus x plus 1 squared. Is that ever going to be equal to 0? No. Because there's nothing I can put in for x, I don't care how big or how small it is, nothing I can put in for x that's ever going to make this denominator large enough to make 2 disappear. As long as there's a constant in the numerator, it's never going to be equal to 0. Now, if there's variable up there, that's a different story. But there's a constant up there all by its little lonesome self. So there's nothing you can divide into 2 that makes 2 disappear. So it's never positive. I'm sorry, it's never 0. In fact, I think what we're going to see is it's always positive. Because even if you get negative number inside parentheses, squared is a positive number. So f prime of x is always going to be positive, which tells you something about the slope. It's always positive. Okay? Is there a place where f prime of x is undefined or does not exist? At -1. Therefore, the only critical number we've got is -1. So I picked out 2 test points, and we'll test them both into the function and see what happens. And my theory is it's going to be positive on both sides, which sounds kind of odd. But when you think about the function in a little while, you'll see why it's true. So if I find f prime of -2, that's 2 over -2 plus 1 squared. And -2 plus 1 is -1, but when I square it, it's positive. So 2 over 1 is positive. That means the function's going up. And f of 0 is also positive. So it's still going up. So our original function was x minus 1 divided by x plus 1. What happens as I come up toward -1 from the left? It's increasing. What happens after I jump over where it's undefined? Is it still increasing? Okay. Believe it or not, folks, when I was in college and taking Calculus 1, we did not have graphing calculators. This was how we graphed functions. We had to know enough calculus to be able to graph the function by knowing kind of what the function looked like and figuring out how it behaved on either side of the critical numbers to be able to sketch a function. It was the pits. So just to verify, we did pretty much exactly what they did. I just did it by hand so you could follow along step by step. And it says to find any asymptotes, but you all know from what we learned before that this original function, that couldn't be 0. So x plus 1 couldn't be 0, which means x couldn't be -1, which was the only critical number that it had. So that's the graph that we got. Now I'm going to caution you about one thing, and this is an important thing. Notice that the reverse of the test for increasing and decreasing isn't true. It is possible, even though we say usually, you know, the function is, if it's going to have a 0, it's going to go negative to positive, or from positive to negative. But the truth is, this function is always increasing, but it still has a critical number at 0. Okay? It does have a critical number at 0, but its tangent at 0 has a slope of 0. Don't assume that just because you found a 0, it's going to decrease on one side and increase on the other, or increase on one side and decrease on the other. Doesn't necessarily happen. So the other two functions showed you that it could increase on both sides of a critical value. But it can also happen with a function that's not undefined at some value, simply that it could be, this is a cubic equation. And a cubic equation is always increasing except for that one instant in time when it flattens out before it takes off going up again. Okay? So don't assume that it always has to be opposites on the sides of the critical number. It doesn't have to. And it doesn't mean that the signs on your derivative have to alternate between critical numbers either. You can have two critical numbers, and maybe for the first one it will go down and then up, but on the other side of that other critical number it may go up again. Okay, so always test. Don't make assumptions that it has to be a certain way. Now you can find the derivative of the function of a particular x value, which you already know how to do. Just remember, and the reason I left this one in here again is there will be places where your calculator will lie to you. If you take a numerical derivative, sometimes it will lie to you. It will tell you that the derivative is some number, and usually it's some outrageously large number, but it'll tell you it's some crazy number when in fact the derivative is not defined at that number. So be careful using the numerical derivative as a check. If you ever have one that causes you to, you know, like, well, that's a crazy number, it's not what I expected it to be. Go back and look at that function. It's entirely possible if you plug that number back into your function The function was undefined at that point. But the calculator doesn't know that. The calculator is only looking at the derivative of the function. It's not paying any attention to the function. So it comes back and gives you all kinds of crazy numbers because what it does is a numerical process. It's great at arithmetic, but it doesn't understand anything. It's only as good as what you put into it and what you know it can't do. And you can also find your maxes and your mins using the calculator. So when we do these, if you're trying to figure out if your critical numbers are right, you can always graph your function as long as you can find your function using that zoom fit feature. You can always graph it and find your maximums and minimums on the calculator and then make sure that matches with what you've got for critical numbers. And of course the question you ought to have is, well, okay, that's nice. What's this good for? Why are we doing this? So here again, we're going to come back to profit analysis. Company selling computers finds that the cost per computer decreases linearly, which means it's a straight line function, with the number sold monthly. It decreases from $1,000 when you didn't sell any to $800 when you sell 1,000. Now what that means is that $1,000 when none are sold, that's the 0.01,000. 0 computers, $1,000. That's a y-intercept. That's B. And since the price decreased by $200, 1,000 minus 800, when you sold 1,000 computers, then the slope is negative 200 over 1,000, or negative 0.2. So your average cost function is right here. This average cost function, you don't have to divide by x because that is the average cost function. That was what it's telling you that it was to start with. So you don't have to find it on this one. Sometimes you have to actually divide the function by x to find it, but on this one it comes out of the problem. And the thing to remember is this is only good as long as x is between 0 and 1,000. They don't know what happens after 1,000. And x is the number of computers sold monthly. So the average cost is actually C of x over x. That means the cost function is given by multiplying, instead of dividing, x times the average cost. So if we multiply x computers times the cost per computer, that's basically what we're doing here. The average cost is cost per computer. And if we have x computers, then x times the average cost will give us the cost function. And our cost function then is 1,000x minus 0.2x squared, and still keeping to the domain restriction of 0 to 1,000. Now before I go on, is that okay with everybody? Everybody understands what we just did? Because if we're talking about cost, and you see the problems about profit, that means there's going to be something more. Okay, we will continue then. Suppose the revenue function is approximated by 0.0008 x to the third minus 2.4 x squared plus 2,400 x. And again, x is from 0 to 1,000. And if you're wondering where they might have gotten that, they probably collected data and fit a model to the data. That's where they came up with that cubic. They probably checked at various points for different months. Now, since this is about profit, and I've been given cost, and I have revenue, how do I find profit? Revenue minus cost. Okay. Since these functions are measured in dollars, starting with 1,000 when they don't sell any, and 800 when they sold 1,000, what kind of profit numbers makes sense? Is profit going to be in the 50-cent range? Okay, is profit going to be in the dollars range? Yeah. Is it going to be in the $1,000 range? Are you going to profit $1,000 per computer? No, so you need to think about that. So the first thing we're going to do is we're going to find the profit function, and profit is revenue minus cost. So you take your revenue function, you subtract your cost function, and you be very careful that you don't mess up the signs. We're all capable of it, including me. It's the little things that get you. So this is 800 thousandths? No. 8 ten thousandths. 8 ten thousandths x cubed minus 2 point, and that is a typo right there. I thought I got all of them out. That's 2 point, no, that is right. That is not a typo. That's negative 2.4 x squared minus times minus is plus 0.2 x squared is where the 2.2 x squared comes from, okay? And then 2400x minus 1000x gives 1400x, and it's still positive. And since we're analyzing profit, what do you think we're interested in? This is your computer manufacturing company. What do you want to know? That's right. I want to know when I'm going to make the most money. I need to know what the maximum profit's going to be. So I'm going to take the derivative of that function and set it equal to 0. So there's the function for the, I'm sorry, I put revenue, but that's supposed to be profit, P of X. And I need P prime of X. So help me out. Okay. Good job. And this is dollars per computer sold. Always keep in mind what it is. And I need to know when my profit is going to be the highest. So I want to know when its rate of change is going to be 0. Okay? And this is going to be just to put it in context, that's the change in dollars profit per computer sold. So, who wants to factor that? I sure don't. So I'm going to say A is equal to 0.0024 and B is equal to negative 4.4 and C is equal to 1400 and X is equal to negative 4.4 and take its opposite, plus or minus the square root of negative 4.4 squared minus 4 times 0.0024 times 1400. And divide the whole thing by 0.0024 times 2. So X equals positive 4.4 plus or minus the square root of something that I'm going to calculate in a minute, divided by 0.0048. I can do that much in my head. And since I know it doesn't matter if it's positive or negative, I get the same thing when I square it. I'm just going to square 4.4. And then subtract 4 times 0.0024 times 1400. And that means I'm taking the square root of 5.92. And then I'm going to take that answer, which I'm going to round off to 2.433, and say 4.4 minus 2.433, and then divide that by the 0.0048. So there's one value. And then 4.4 plus 2. Whoops, got to back up. It's 2.433, not 22. Let me try that last one again. So instead of 412, it's about 409.79. And 1423.54. Now, what does X represent? What is X counting? Number of computers. Can I have 0.79 of a computer? Don't think so. Can't have 0.54 of one either. So I would assume that I need to round those off. So that tells me when I'm making around 410 computers, I have a critical value in my profit. Do I know if it's the maximum or the minimum? Your brain probably wants to tell you that's probably the good one. You don't know. These are the zeros, remember. This is when you're making, your profit has temporarily stopped increasing or decreasing. One is a max, one is a min, but don't just assume which one is which. We still test. So 409.8 and 1423.6, we're still going to choose test points. And if this is on a number line, then one really easy test point, what happens if I don't make any? And then, let's see, and in between we've hit 1,000. Now, do I care what happens after this? Oh, sorry. Thank you. So this is where it comes to a peak. This is a 0. This is also a 0. Question is, what happens before you get here and what happens after you get there? Because if this is increasing and then decreasing, then, you know, we have to see. So this means we go back and evaluate the derivative at both of those places. And at this place, here again, I want to use my calculator. But I'm feeling lazy now. So I'm going to put the original function in. Because I want to know how much profit I'm going to make at the end. But since I also want the derivative, I could either enter in the derivative or I can use nderiv. I'm going to enter in the derivative. So what I have in y1 is the function, and what I have in y2 is the derivative of the profit function. And I want to know what happens to the profit when they don't make any computers. So I go to yvars, function, wrong one. Yvars, function, y2, because I want the derivative. And what is the derivative when x is equal to 0? It's 1400. Shouldn't have even needed to do that. I mean, I know what 0 does to x is it makes it drop out. Okay, what about 1,000? It's negative. And if you want to completely test out the theory, we'll go ahead and do 2,000 since 2,000 is on the other side of 1424. We're back to positive again. So here's what's happening. The function is positive. negative, positive. Your function's increasing, peaks out, decreases, bottoms out, and then increases again. Which is what you would expect this to do because it's a cubic equation. So where's my maximum profit going to be? Around 410 computers. Because after I make 410, my profit drops back down to 0 until I make more than 1,400. Or more than 1,424 actually. And what that means when you plug this in is that when no computers are sold monthly, the profit is going up at $1,400 per computer. Because P prime of 0 is 1,400. And when you sold 1,000, the profit's going down at a rate of $600 per computer. Now this doesn't talk about what happens after 1,000, even though I did plug in $2,000. Why does what I plugged in at the end not make any difference? What was the domain of the original function? It was 1,000. They only knew that those numbers worked up to production and sales of 1,000. They don't know what happens after 1,000. They know it was going down at that point. Now logically, if you're in business and you know that your profits are going down and have zeroed out at some place, do you keep on making the computers? No. So they've decided long before that to stop making computers so that the profit will stay high. So what happens here on the graph says the profit's increasing when 0 to 409 computers is made and sold. The revenue is increasing the whole time until you get to 1,000. Their cost catches up with revenue at that point. And what you see happening with the revenue is that the revenue is going to come back down after that. And your cost is still going up. So your profit has hit a 0 point right here. Because this is where cost and revenue are the same, which tells you you're making 0 profit. And you make your most profit where your profit curve is maxed out, which is when your revenue is actually, this is where the greatest difference between revenue and cost is, because that's that length of that line from the red line to the blue line. That's how much profit you're making. That's when your profit margin is the widest. Okay? You're still making money after $409, but you're not making it as fast. That's really what's happening. You're not losing any money up to this point, but you're not making it as fast. Your profits are starting to dwindle off. Okay? And that's it for section 13.1. Let y'all take a few minutes break.